Now let's discuss this very important point regarding atomicity. So atomicity, that is equal to Cp by Cv for monatomic gases, for example helium or argon. The value of gamma, that is atomicity, is basically equal to 1.66. We have divided Cp by Cv, then the answer comes out to be 1.66 for monatomic gases. Next, for diatomic gases like H2 and O2, the value for gamma, that is equal to 1.4. For triatomic gases like CO2 and H2S, the value for gamma is equal to 1.3. So these three are very important values of gamma for monatomic, diatomic and triatomic gases. These 3 points are important for entrance exams like JEE Mains and NEET. Now let's discuss about the graphs of exothermic and endothermic reactions. The first graph we have plotted between enthalpy and progress of the reaction. Now if we consider reactants as well as products in this case, so the delta H is basically equal to Hp minus Hr, that is the enthalpy of products minus enthalpy of reactants. We can clearly see that product enthalpy is less as compared to reactant, so overall answer is negative, that is for exothermic reaction. Now for endothermic reactions, the value of product is greater as compared to the value of reactant, so the overall answer is positive, that is for endothermic reaction. So these are two graphs for exo and endothermic reaction. Now let's discuss about the limitation of the first law of the thermodynamics. The limitation of first law of the thermodynamics says that it provides no information about the spontaneity of the reaction. It provides no information regarding the spontaneity of the reaction. Now let's discuss about what are spontaneous reaction. Now let's discuss what is a spontaneous process. Any process which under some given conditions that may take place by itself or by initiation and is independent of the rate, that is termed as a spontaneous process. Now let's discuss about the examples of spontaneous processes that take place by themselves. The first one is the dissolution of the common salt in water. The second one is the evaporation of water in any open vessel. The third one is the flow of the water down a hill. The next one is cooling down of cup of tea, that is the flow of the heat from hot end to the cold end. The next one is the reaction between nitric oxide NO and O2 to form NO2. And the last one is reaction between hydrogen and iodine to form HI. Now let's consider the examples of the processes which can take place on initiation. The first basic example is the lighting of the candle. The second one is the heating of calcium carbonate. Calcium carbonate dissociates to form calcium oxide and CO2. The third one is the reaction between hydrogen and oxygen. In the presence of electricity, it can form water. And the last one is combustion of methane to form CO2 and H2O. These are the reactions that take place on initiation. Now let's discuss what is a non-spontaneous process. So a process which can neither take place by itself nor by initiation, that is called as a non-spontaneous process. Let's see the examples of non-spontaneous process. The first one is the flow of the water up a hill or flow of heat from cold body to hot body. So now what is the driving force for any spontaneous process? So basically it says that two forces are important. The first one is the tendency for minimum energy and the second one is the tendency for maximum randomness. These are the two driving forces. Number one is the tendency for minimum energy and another one is the tendency for maximum randomness. Now let's discuss about the limitations of the criteria of minimum energy. There has been found that few reactions are there in the case like evaporation of water or melting of ice, in which delta H is not negative. In the case of evaporation of water, the delta H of reaction comes out to be plus 40.8. The value of delta H is not negative here. Similarly, in the case of melting of ice, the delta H fusion comes out to be plus 6. Again the value of delta H is positive. So there are endothermic reactions that has delta H positive value, but still they are spontaneous in nature. Similarly, decomposition of calcium carbonate is another example. Second example is there are reactions in which delta H is equal to 0, but still these are spontaneous processes. For example, esterification. And the second important example is the expansion of an ideal gas into vacuum. This is very important for school exams. Now let us consider a compressed gas and we have a insulation provided. So insulated vessel, in the case of insulated vessel, Q will be equal to 0 and P external is equal to 0. So we know that W is equal to negative of P external into delta V, that comes out to be equal to 0. So according to the first law of thermodynamics, delta U is equal to Q plus W. Q is 0, W is 0, so delta U will be 0 as well as delta H is also equal to 0, but still the process is spontaneous in nature. Another example is the reversible reactions. Now in the case of reversible reactions, if one step is endothermic, then the reversible step is exothermic in nature, still the processes take place. So that is a spontaneous process, and there are many reactions in which delta H is negative, still they are not spontaneous. So we can say that energy factor or the enthalpy factor, it cannot be the sole criteria for predicting the spontaneity or feasibility of the process. So this can be asked in school exams. So moving on to our next driving force, that is a tendency of maximum randomness, or we define randomness as entropy. Now we know that in the case of gases, the molecules are far away from each other. So entropy of gas is maximum, then comes the liquid, and the last one is the solid. So if we consider the melting of or vaporization of water, so H2O liquid converts into H2O gas, the entropy increases. Similarly, melting of ice, solid form gets converted into liquid. Similarly, here in this case, 1 mole of H2 forms 2 mole of H, again the entropy is increasing, the randomness is increasing. Now what is the limitation of the criteria of this maximum randomness? Liquefaction of gas or solidification of liquid won't be possible if it is the sole criteria. So this is the limitation of maximum randomness. Now let us discuss these points by taking these examples. When the net driving force is in forward direction, so we say energy factor is in the forward direction and randomness is again in the forward direction. We consider driving force to be in forward direction. Now there can be B case also, in which energy is in forward direction but randomness is in backward, but it is having less magnitude, so overall driving force is in forward direction. The third case can be energy is in backward direction but randomness is in forward direction, having more magnitude, so the net driving force is in forward direction. Now let us discuss the type 2 form, when the net driving force is in backward direction. So the first case is if energy is in backward direction and randomness is in backward, so driving force will be backward. Second case is if energy is in backward having larger magnitude but randomness is in forward, so net driving is again in backward. Energy is in forward but randomness in backward having more magnitude, so net driving is again in backward direction. Next is the type 3, when the net driving force is equal to 0, so both energy and randomness, they are having same magnitude but having opposite direction, so the net driving force is equal to 0. So we can explain the evaporation of water here. It changes into liquid to gas but having delta H is equal to positive of 44. So energy factor opposes here, but our randomness favors because it is moving from liquid to gas. Randomness is increasing. So now let's properly define what is entropy. So it is basically the measure of randomness or disorder of a system. So delta S can be written as a product minus reactants, or I can say that delta S is equal to Q reversible upon T, that is temperature. So entropy change during a process that may be defined as the amount of the heat that is absorbed isothermally and reversibly divided by the absolute temperature at which this heat is absorbed. So it is very important point to note down here that it is an extensive property. The units of entropy change are joule per Kelvin per mole. Now let's drive an expression which shows that entropy is a state function. Now suppose there is a system that absorbs heat isothermally and reversibly at any temperature T. We have a system and a reservoir here, and it is expanding from, let us say, V1 to V2. So the change in the entropy of the system that is given by delta S of system is Q reversible by T. So the equivalent amount of the heat that will be lost by the reservoir. So the change in the entropy of the reservoir, this will be equal to minus of Q reversible by T, because heat is lost in this case. So there is negative sign. So the total change in the entropy that will be equal to delta S1 system plus surrounding, that comes out to be equal to 0. So in this cycle, delta S1 in the case of expansion comes out to be equal to 0. Now let's consider the case of compression from V2 to V1. So system is minus of Q reversible by T, but reservoir will be gaining. So it is Q reversible by T. Total entropy change will be equal to again 0. Now if we calculate the total change in entropy for the complete cycle, so complete cycle will be delta S1 plus S2, that comes out to be equal to 0. So it is a state function. Next, there are few definitions. The first one is the entropy of fusion. So this can be written as delta H of fusion by melting point, that is entropy of liquid minus entropy of solid. Then is the entropy of vaporization, that is delta H vaporization by T temperature. Here we have entropy of vapors minus entropy of liquid. Next is the entropy of sublimation. Now entropy of sublimation is equal to delta H of sublimation by T. Again S is for entropy of vaporization minus entropy of solid. So let us consider few examples more. 2 moles of sodium bicarbonate dissociates to form sodium carbonate, CO2 and water. The number of moles are increasing, so entropy is increasing. So whenever a rubber band is stretched, so what will be the entropy change? You can think about it. Next is an egg is boiled. So what will happen? Entropy will increase here because of denaturation. So we can say that delta S for universe, or the total delta S, total entropy change, that is basically equal to system plus surrounding. So all the spontaneous processes, they have some positive value of total energy. This is very important point to note down here, that total entropy change will be greater than 0 or positive, or total entropy or entropy for universe is negative if it is a spontaneous non-spontaneous process, and if it is equal to 0, then the reaction is at equilibrium. So 3 points are very important for any spontaneous process. Delta S total should be positive, for non-spontaneous it should be negative, for equilibrium it should be 0. Now entropy change during adiabatic expansion, reversible adiabatic expansion, for adiabatic Q is equal to 0. So delta S comes out to be equal to 0. This is known as isoentropic process. But for adiabatic free expansion, delta S is not equal to 0. This is a very important point to note down here.